Welcome to MRI Physics for X-ray students. This is the next step up from our short video, MRI Physics for 5th graders. Let's jump right in. 1. Atomic basis. Why hydrogen matters. The human body is 70% water, rich in hydrogen nuclei. Why protons? A proton has spin angular momentum, has charge. Therefore, it creates a magnetic moment, acts like a tiny bar magnet. This combination, spin plus a charge, is what makes MRI possible. On to number 2, external magnetic field, B0. We are going inside the MRI scanner now. A strong static magnetic field, B0, typically 1.53 Tesla, is applied. So what happens to protons when your body goes inside the magnetic field? They align in two energy states, parallel low energy, anti-parallel high energy. There are slightly more in the low energy state, creating a net vector called net magnetization vector, NMV. On to number 3, precession and Larmor frequency. Protons don't just align, they precess, wobble around the magnetic field. The frequency of this motion is given by the formula in the top right corner. The Larmor frequency equals magnetic field strength. Key insight: stronger magnet, higher frequency. Number 4, resonance, energy absorption. MRI uses radio frequency, RF pulses. If RF energy is applied at exactly the Larmor frequency, protons absorb energy, transition from low to high energy state. They become synchronized, in phase. This is resonance. We are halfway there. Hang in there, it's just starting to get fun. Number 5, flip angle and transverse magnetization. The RF pulse causes the NMV to tilt away from B0. 90° pulse, magnetization moves into transverse plane. This creates detectable signal. Number 6, signal generation, Faraday's law. As transverse magnetization precesses, it creates a changing magnetic field. This induces voltage in a receiver coil. This voltage equals MR signal. Are we having fun or what? You are doing great. 7. Relaxation, return to equilibrium. After the RF pulse is turned off, protons relax via two independent processes. T1 relaxation you see on the left, and T2 relaxation on the right. Let's dig into T1 relaxation because you probably already learned about T1 weighted image. Energy is transferred to surrounding tissue, and longitudinal magnetization recovers. Defined as time to recover some 63% of original magnetization. Notice the clinical part. Fat has a short T1, so fat will be bright on a T1 series. And water has a long T1, so it will show up dark on T1 series. Now for T2 relaxation or weighting. Loss of phase coherence between spins occurs and transverse magnetization decays. You can think of T2 effect as sharing of energy with its neighbors until they return to their normal state. So tissue that is tightly packed like a muscle. The energy is shared quickly, but water is spread further apart, so they share much slower, which is why water is bright on T2. We are in the home stretch with number 8, key MRI timing parameters. These control image contrast. TR is your repetition time. It is the time between RF pulses and controls T1 weighting. What about the TE? The TE is the time to echo. It is the time to measure signal, and it controls T2 weighting. In summary, TR is the time between RF pulses and controls T1 weighting. TE is the time to measure signal and controls T2 weighting. A short TR will have more T1 contrast, and a long TR will have less T1 contrast. And a short TE will have less T2 contrast, while a long TE will have more T2 contrast. Number 9, image contrast. MRI contrast comes from differences in T1, T2, and proton density. Proton density. By adjusting TR and TE, we emphasize T1 weighted images for anatomy, T2 weighted images for pathology, fluid. Congratulations, you made it to number 10. Spatial encoding, how images are formed. So far we have a signal, but no location. MRI uses gradient magnetic fields. Imagine you are laying inside the MRI machine. It might help to close your eyes to imagine this. To the left and right of you, to the front and back of you, and from your feet to your head. These are the 3 physical locations of the gradients inside the machine. and we can vary energy between them to uniquely locate where we are looking in the body. Stick with me now. So if you want to get an image cross-section image or an axial, you would use the head-to-toe gradient for slice selection because we want to make each slice location unique. Gradients slightly change the magnetic field. Now think about playing the game Battleship Where to Win. You have to guess the coordinates of the ship. B12. The other two gradients not being used for slice selection are used for frequency and phase encoding. Think about a coronal image of your body. You would want to geolocate the anatomy using the gradients on your left to right and head to toe. This spatial information is stored in K-space and reconstructed mathematically, Fourier transform. I hope you liked the 10 steps to MRI physics for students.